Okay, everybody, in this video we're going to be starting our module on polynomial functions, but specifically in this set of videos we're going to be discussing quadratics only, which is just a particular type of polynomial function, but then from there we'll kind of expand it to all polynomials. So let's go ahead and take a look at what we mean by polynomial in the first place, and as one might infer, the prefix poly, poly, just means many. So we say many, and then nomial, okay, so we say nomial. And when we refer to nome, just that root structure there, we just like name, a many-named thing. So we say a many-named function. In other words, we say something that has many terms to it. And I know there's more to it than that, and we can get into the specifics later. But essentially, if you've been taking an algebra course or like a pre-calculus course, you've seen some polynomial functions already. These would be some things like I've got listed here, but we say f of x equals ax plus b, or y equals mx plus b. That'd be our linear function, but that is a polynomial, as a matter of fact. We have a constant function where y equals just a number is a horizontal line, and also our squaring function, which is, if you graph it, a parabola. But these are all examples of polynomial functions, and not so much what makes them polynomials right now, as much as we've seen some before and they all have some things in common. So let's go ahead and start to talk about how do we define polynomial functions in general. And so we have here this definition. We say let n be a non-negative integer, okay, integer meaning it's a whole number, positive, negative, or zero, such that all of these terms right here are real numbers, such that a sub n, subscript n, cannot be 0. Okay, and we'll talk about what a sub n in here is. But we say the function is given by this. F of x equals this big long chain of things. I just want you to notice some things here right off the bat. But we say a sub n right here. A sub n, we might as well classify this as the leading coefficient. Okay, so we're always looking at leading coefficients, but we say, remember, a sub n cannot be 0. We just say it's a polynomial function where the leading coefficient is not nothing, which is fun to say. We also have a sub n is taking times x to the n. You notice the next term is just a sub n minus 1. So I just want to point out here, if n was like 3, this is our leading coefficient of the a sub 3 here, then this would be x to the 3. In other words, if you look at the next term, it'd be a sub n minus 1. Well, if n is 3, we'd say a sub 2. And then x to the power of n minus 1, it'd be x to the 2. Essentially, this whole long chain of terms right here, just is saying kind of like when we write polynomial functions, for instance, if I just make one up here, we often write it like this. We could just say negative 4x to the 5th plus 3x to the 4th minus 2x squared plus x minus 10, where we just kind of basically like to list them in decreasing order till we get down to this constant term. You'll notice here in the definition it says a sub 0. We could have written an x to the 0, but recall that anything to the power of 0 is equal to 1, so we just tend not to write it. But we say this is what a polynomial function is, where all of the coefficients are real numbers, and by the way, n is an integer, so all of our powers are whole numbers as well, and they are non-negative. So that is, we wouldn't have a function that says this, negative 4x to the 3rd. This would not be a polynomial function because, or the negative third, excuse me, negative third, because this is a negative integer power, and also this wouldn't be, negative 4i x to the positive 3. This would also not be a polynomial because we say all the coefficients have to be real numbers. But simply put, we say polynomials are these things. Now, I mentioned in this video we're going to be discussing specifically quadratics. So before we do so, let's go ahead and have a real quick conversation about the degree of a polynomial. You notice here I write, we classify polynomials by their degree, but the degree, if you look back up here in our definition, let me switch colors here. The degree is always kind of just the highest power of x. So we would define it as being n here. And you notice that's in the definition. We say it's a polynomial function of x with degree n. But we say, for instance, a constant function is of degree 0. That is, we say y equals 4. This would be degree 0, and the reason why is because I could write this as y equals 4x to the 0, where this was the biggest power. We could define another function. We say a linear function is of degree 1. Well, this could be something like 2x plus 3. With the highest power of x here, again, is our degree, and that is 1 in this instance. And, we're going to be talking about in this video quadratic things. Well, I'll go ahead and spill the beans, but the squaring function, I say 3x squared. I'm just making this up here. But its highest power of x is 2. So we say that is the degree. And anything of degree 2, we say is quadratic. So let's go ahead and define quadratic things. I start by here giving us some examples of quadratic things, but as I mentioned previously, we're going to be studying or discussing only quadratic functions. We say these are things that are polynomials, but specifically of degree 2. That is, the highest power of x is going to be a 2. But these are all right here examples of quadratic things. You notice here, I've got my power of 2's out front. This is a very, very common looking, if we graphed it, it'd be a parabola, but common looking quadratic thing. And then also this, if you've been studying function transformations, we look at this as having like an a value, an h value, a k value, and we'll dig into those deeper. But also over here we have a quadratic. The highest power of 2 is 2, the highest power on an x. And then last but not least, m of x here. I want you to notice this, m of x. If you were to FOIL this back out, the interesting thing is we have two binomials being multiplied, and they are individually on their own first degree things. But if you took a first degree times a first degree, you end up with a second degree thing. And if FOILing this out, actually, you get x squared, it'd be plus an x minus 2x, and then minus 2. In other words, we get x squared plus a negative x, if you will, and then minus 2. But this would also be quadratic. Okay, so if we want to strictly define quadratic functions, then we often do it thusly. So we say f of x is some quadratic polynomial here, but it's of this form where a, it looks like a is our leading coefficient here, leading coefficient, we can abbreviate that LC, is not 0, but we say ax squared plus bx plus c, where c is our constant term. We'll refer to this as a quadratic function. And so these are so particular that we're going to go ahead and start to talk about the anatomy of their graphs and what we call their graphs. But we say the graphs of these functions are these fun things you do in algebra. They are U-shaped, and we refer to them as parabolas. Okay, so these parabolas, we can model lots of real-life situations using parabolas. So if you were to discuss, like, this is my satellite dish here, and it's got a little axis in the middle, and it's broadcasting a signal at the top. Interesting thing is, like, if you had anything flowing into the dish parallel to the axis here that's coming up in the middle, it actually reflects right back into the axis, which is kind of a cool property. But we also model things that fall with gravity, right? Goes up, comes down with parabolas. So if that's the case, let's go ahead and discuss some basics of the graphs, and we'll be done with this video. But we say the anatomy, okay, first of all, and properties of parabolas. First things first, we want to recognize this. All parabolas are symmetrical about a vertical line, okay? We say this vertical line passes through their vertices, which is the plural of vertex, but we're going to refer to this as the axis of symmetry. And so you notice down here I've got two parabolas already sketched, and I thought I had one going upside down. That's okay. We could say an upside down one here. But you'll notice here in both of these, or maybe this one I've just sketched in here, we say there's a vertical line running right down the middle of it, and it has to go through what we classify as the vertex, which is kind of the apex of the curve. Okay, so that's the next point I want to make here. It says the point where the axis intersects the parabola is referred to as the vertex of the parabola. Remember, the plural is vertices. But it's also important to note this. The vertex is always either at the maximum or the minimum point on the parabola. So a parabola either has a maximum or a minimum, but does not have both, because let's say if it has a minimum, notice that it keeps going up and up forever, so it would never have a maximum, but could have a minimum. And if it were to go down and down forever and ever, it would have a maximum, a max, but no min here, okay? And then last but not least, and this is really important, but we say if the leading coefficient, which we've been calling a in our ax squared plus bx plus c, if it is positive, okay, then we say then it opens upward. So we say a positive implies that it looks like this. It goes up. And if a is negative, it implies that it opens downward, okay? And also important to note, if it's negative, it has a max, and if it's positive, it has a min. So these were in general kind of parabolas over here that I've sketched in. The last slide I want to look at here is we say the simplest form of a quadratic function. But we say is anything is just a times x squared, where a can be positive or negative. Of course, we already know we've classified a as not being 0. But take a look at my two parabolas that I've got sketched in here. This is just the graph of y equals x squared and y equals negative x squared. But you notice that the vertices here on both of these are automatically at the origin, 0, 0. And I've made the note that if a is positive, the vertex is at the point 0, 0, with a minimum y value at the origin. And if a is negative, then the vertex is the point 0, 0, should say 0, 0, with the maximum y value on the graph, as we show here. And so I'm sure we want to be done with this video, but just very, very quickly, what we'll do is we'll pop over to GeoGebra. I'll throw in a slider. So we say slider is this thing I can adjust from -5 to 5 in this instance. But let's put in a function, and we'll call this function f of x, but we say it's a times x squared. We'll mess around with this a value. And you notice up here we say the a value is 1 in this instance. But also notice that it starts at the origin, and I just want to point this out. We'll drop in the line x equals 1 here and put an intersecting point on these two things. So we say intersection of that line x equals 1 in my parabola. We say it does indeed start at 0, 0, but notice with an a value of 1, that is 1 times x squared, if you were to put that a value over a 1, it kind of tells you how to get from the vertex to this next point on the graph, which is 1, 1. Because I would go up 1, right 1, if we kind of think of it as a slope. But as I adjust a is getting bigger and bigger, you notice that our parabola gets steeper and steeper. If I made a like 3, from the vertex I would go up 3, right 1. Remember I said we could take that a value and place it over a 1 and think of it as a slope. But up 3, right 1, and then the negative a value, of course, would go down. In this instance, I say down 3, right 1 from the vertex, and goes through 1, negative 3. But also, this. If the a value were to be something, for instance, like a half, 1 over 2, you would not go up 1, right 2 to get to the next point on the graph. As a matter of fact, I said, let's put the a value over 1, look up here. If the a value is a fraction of a half, rewrite it as a decimal. We say 0.5 over 1. That's just going to tell me that from my vertex, I am going to go up 0.5 units every time I go over 1 to get the next point on my graph. But that a value is just a really, really kind of a interesting way to tell you kind of how your parabola opens. Cheers.